This is complex analysis. This will be a series of 2 sessions on extended complex plane. What we plan to do is we are going to attach an extra point to this field of complex numbers or complex plane, and that extra point is usually called a point at infinity. Then we are going to put a topology on this new set, namely C union the singleton infinity. Okay, especially we have to only define when a set which contains infinity is open. Okay, then we will get a topology with respect to which it will be compact and Hausdorff, but we will not stop to prove that. But what we will concentrate on is if I am given a function f from an open set containing infinity to see when it is continuous. Okay, we will try to understand and look at some examples, and we will reformulate this, okay, in terms of homeomorphisms. Okay, that will play an important role to generalize it to holomorphic functions. That is, in the next session we will also talk about when a function from an open set containing infinity to C is holomorphic on that open set. Okay, and with a word of not caution, some, okay, a remark. Usually when they do the extended complex plane, all textbooks will talk about Riemann sphere. Why? Because when Raymond created this, okay, he wanted to talk about some kind of topology. Okay, he wanted to understand it in somewhat concretely. But at that time, the topology didn't exist. In fact, topology originated from the seminal ideas of Riemann. When you wanted to talk about Riemann sphere and when you wanted to talk about Riemann surfaces for multivalued functions, okay, they were the actual genesis of topology. But at that time he didn't have, so the only way that he can explain to others is thinking of this C union infinity as a sphere in R3, the unit sphere in R3. Okay, and believe me, for most of complex analysis I don't have to establish this, because once I know how to put a topology on C union infinity, okay, that's good enough for me. At that time he did not know, so he set a bijection from C union infinity to the sphere, and then he said the topology on C union infinity. Again, remember the word topology didn't exist at the time. Okay, is same as the topology on the unit sphere, which comes from the inherited topology from R3 by metric. Okay, please keep these ideas in mind. Okay, and for exam purpose and various other reasons, you may still need the notion of Riemann sphere. There will be a series of lectures, I think 2 lectures, on the one-point compactification of any locally compact algebra space and its application to Rn, and in particular to R2, which is essentially complex plane. Okay, so we will put everything there in very concrete terms with a lot more detail than you will find in any topology book or even in complex analysis book. Okay, so rest assured you will learn it, but not in this course. Okay, right. So if you are ready, we will go to our thing. So we have C, and then we want to attach an extra point. Okay, I can call it a star, I can call it this, I can call it this, I can call it a, like this. Usually it is called point at infinity. The infinite symbol read as point at infinity. Okay, so we are going to take a new set C union singleton infinite. This is called extended complex plane. Okay, now just 1 second. There are limited arithmetic operations on C infinity. We will not discuss it now. We don't need it now, so I do not. What I want to concentrate more on the topology of C infinity, right? So essentially, I want to say when U contained in C infinity is open. Okay, if U is actually a subset of C, then U is open. So I want a topology tau infinity on C infinity. Okay, if U is already contained in C, then U is open in C infinity if and only if U is open in C. This is the first criterion. And second thing, suppose infinity to belong to U, I want to say U is open in C infinity. Then what I look at C minus U. Okay, or let me say U if and only if U is of the form V union singleton infinity, where V is contained in C is open in the standard topology and C minus V is compact. Okay, I will give picture for this so that you will have some kind of an idea. Okay, so what I have is this is my complex plane and my point at infinity is somewhere, right? So what I do is I take some compact set. Okay, K is a compact subset of C. Now let's look at V, which is C minus K. Since compact set is closed, this is going to be open in C. Okay, open in C. Then how do I form U? I form U union singleton infinity. Okay, so let us look at. So what is the set U is all these fellows. So let me use a different color scheme. Okay, in all this point including the point infinity, that is the thing. So essentially what does it mean? You take a compact subset of C, take the complement and include the point at infinity also, that's an open set. Okay, then what is known, we are not going to prove that, as I said. Okay, so tau infinity consists of tau, that is a topology on C, standard topology on C, union all sets of the form V minus singleton infinity, where V suppose is open and C minus V is compact. Okay, this is actually in modern topology, it's known as one point compactification. I will not stop to do all these things. Okay, so watch my video on this topic. Okay, so it is, one can actually prove that tau infinity is compact and Hausdorff. Okay, right. If necessary compactness, I will prove, because I may need at one point to use the topology tau infinity is compact. But for the time being assumed, today what we all know is I know how to identify open sets containing infinity. Okay, remember how does it look like? Again, pause, review. Okay, so you should have this kind of picture. I have a C, I have a compact set, take away C, sorry, take away the compact set from C, then add infinity. Okay, the green area is the one along with infinity. Okay, keep that in mind. So pause, review, proceed. These things are also proved in my book. Okay, if you want, but believe me, we don't need this at present, so let's not worry about it. Let's go ahead. Okay, so this is a topology. So using this topology, First, there is a basis. Okay, I want to find a local basis of open sets at infinity. What does it mean? Okay, so I want look at the collection. See, what are the simplest thing like compact sets? You can see if I take the closed balls B0n. Okay, this is a closed ball. Okay, and we know this is compact, right? So let me look at un to be C minus a closed ball, okay, and union infinity. And this is open, okay, this is an open set containing infinity. Is this clear? Now I am claiming this collection un is a local basis at infinity. What does that mean? So let u, okay, contain infinity be open in C infinity. Then what do I want to say? Okay, then I want to say there exists a un such that infinity of course belong to un and it is contained in u. This is what we want to prove. Okay, that is very easy. Suppose u is open, then u is of the form B union infinity and K is C complement B. Since K is compact, okay, and let's look at B0n, the open balls, as n where is, this is an open cover of C and hence of K also. And notice that this is an increasing cover, that is B0n is contained in B0R if n is less than or equal to R, where R is a natural number of course. Okay, yeah, right. Therefore, since K is compact, there is a finite subcover, call it B0n1, B0n2, B0nk, but choose n to be the maximum, then therefore there is a unique thing so that B0n is contained in K. But this fellow in turn is contained in the closed ball B0n. You understand that? Since K is contained there, therefore C minus K, the complement contains C minus B0n, which is your un. Okay, so which is not un, which is okay, okay, this content. Therefore, and my u is C minus K union infinity, okay, union infinity. Therefore, this contains C minus B of 0n union singleton infinity, which is un. So, if I want the, okay, so this collection un is a local basis. So, what is the use of that? See, whenever I want to say let U be an open set containing infinity in C infinity, I can as well consider this some un for some n. Okay, and all topology analysis can be done using this. The way you use metric space. See, in a metric space, even though you have topology, it's easier to use open balls. In fact, it's even easier to use balls of the kind bx 1 upon n rather than bxr for any r positive, right? So they play, uns play the role of such things, bx 1 upon n. Okay, keep that in mind. Okay, now let pause, review, proceed. So let us try to understand continuity. Suppose f is defined from u to in C infinity to C, and let us say C is u and u is in tau infinity. This is open, right? I want to know when f is continuous at infinity. This is what I want to understand. Now that there is a topology, is much easier. So what does it mean? That means, okay, look at f infinity. This is a point in C. Okay, call it alpha. Then let's look at, for any given epsilon positive, let's look at b alpha epsilon. Then I have to find there exists an open set u or un containing infinity, so that f of un is contained in b f infinity epsilon. It could be any open set also. Do you understand this? Yeah, this is the definition of continuity. Yeah, so let us use that just to try to understand this. This means what? Let us try to understand this statement. That means there exists an n, a natural number, so that for every z in C infinity, okay, whenever mod z is greater than n, okay, fz minus f infinity is less than epsilon, and when z equal to infinity, okay, f infinity minus infinity will be 0, that is less than epsilon, will be obvious. Okay, therefore if you want z not equal to infinity and mod z. Okay, then so f is continuous if and only if at infinity, if and only if this happens. Given epsilon positive, there exists n in n such that blah blah blah. This one you have to write. Okay, pause, review, proceed. Okay, let us look at very specific examples now. So let my u be C star non-zero complex numbers union infinity. This is an open set containing infinity by very construction, because this is your v is C star, its complement is singleton 0, that's a finite set and hence compact, right? Therefore this is open. Now I want to define a function from u to C. Okay, if z is not equal to infinity, I want to define f of z equal to 1 by z. Of course z is in u. Now remember, f should be a function on u, therefore I should know, I should define f infinity also, that must be a complex number. So, and I want to produce a complex number so that the function f is going to be continuous at infinity. What will be your choice? I'm sure all of you know that, right? 0. Okay, by intuition you know that, but we want to prove this rigorously. So we want to claim is f continuous at infinity. So let epsilon be given, right? Then what do I want? I want to find some n so that something happens, but let's look at estimate. Okay, if you have gone through my videos on analysis, continuity, etc., I will not worry about delta immediately. Okay, I will not worry about anything. I will simply say what I want to estimate. I want to estimate f infinity. Okay, this I want to show less than epsilon whenever z satisfies some condition. If z equal to infinity, there is 0, so I do not worry about. So let me assume z is not equal to infinity. Now what is this? Therefore 1 by z, f of z is 1 by z minus 0. Okay, so I want this to be less than epsilon. So what does that mean? That means 1 by mod z or 1 by mod z should be less than epsilon, right? Remember z is in not infinity and z is in C star, therefore, okay, therefore that is the same as saying mod z should be greater than 1 by epsilon, right? Right? So if you want n, what do you think I will do? By Archimedean property, choose n so that n is greater than 1 by epsilon, right? Therefore mod z is greater than n, but n is greater than 1 by epsilon, right? You understand? So I claim So what is our un? We are going to claim f of un is contained in b0 epsilon. That will prove continuity of f at infinity, right? So let's take z in un and z not equal to infinity. As I said, when z is infinity, f infinity minus infinity will be 0, so I have nothing to prove. Therefore it's going to be, I'm just writing the proof. This is going to 1 by mod z. Remember, mod z is greater than n, therefore z is 1 by mod z is less than 1 by n, yeah, and 1 by n is less than epsilon, yeah. So claim is proved. Therefore f is continuous at infinity. This is all very easy, and if you learn my the concept of limits etc. from my real analysis courses, you will see that's exactly similar. Okay, you should be very happy you had already seen it in some sense. Except we are dealing with complex numbers, and in real analysis there will be two infinity. Here there is only one infinity. Okay, now let's look at a second example. Okay, let us do a f of z equal to, let me write z plus 1 by z minus 1. Therefore my domain U should be C minus singleton 1 union infinity. Therefore this is an open set containing infinity, right? So this is for z in U, but z not equal to infinity. So I have to define what is f infinity. Again you can use intuition, right? So as z tends to infinity, z plus 1 by z minus 1, where do you think it should go? Intuitively it should go to, yes, 1. So we want to know whether f is continuous at infinity. So what is that I have to estimate? I have to estimate f of z minus f of infinity, which is mod z plus 1 by z minus 1 minus 1, that is equal to z plus 1 minus z plus 1 by z minus 1, which is equal to 2 by mod z minus 1, right? So what I want this fellow should be less than epsilon. So if I want to prove continuity, so somebody has given me already epsilon positive, so I want to find conditions on z so that this fellow is less than epsilon. But now that's again easy, right? Again, if you have learned analysis from me, so I want, whenever I want to prove some alpha is less than a, what I do is I will try to find alpha is less than or equal to beta, and that beta, if I prove that beta is strictly less than a, then it will follow, right? Therefore 2 is okay. 1 upon mod z minus 1, I want to say is less than something, a beta I want to find, right? That means for 1 upon mod z minus 1, I want to say is less than or equal to something, then what I should do is I should find a lower bound for this. I want an upper bound for this. Okay, that means I want a lower bound for this, equal greater than this. That is very easy. Triangle inequality tells us. What does it say? It says mod z, yeah, is less than or equal to mod z minus 1 plus mod 1, which is 1. Therefore mod z minus 1 is greater than or equal to mod z minus 1, right? Yeah, and so suppose this is positive. Okay, let's assume mod z is greater than 1. Remember, we are looking for z from a neighborhood of infinity, from an open set containing infinity. That means some, okay, it will be far away, right? So mod z I can make it far away. Therefore I can as well assume mod z is greater than 1, so that this remains positive, right? Okay, therefore 1 upon mod z minus 1 is less than or equal to, or 2 upon that is less than or equal to 2 upon mod z minus 1. Okay, this is your f of z minus f of infinity modulus for z not equal to infinity, right? And z not equal to 1 also, of course. Okay, this I want to be less than epsilon. Now remember, I made sure mod z minus 1 is positive, therefore I can take inverse thing, right? If 0 less than a less than b, then 1 upon a is greater than 1 upon b. So I can use that. Therefore mod z minus 1 by 2 is greater than 1 by epsilon. Therefore mod z should be greater than 2 by epsilon plus 1. Right? So what do you think I will do? So if I take this u to be set of all complex numbers z in C such that mod z is greater than 2 by epsilon plus 1, right? So of course epsilon you can take to be less than 1, etc., something that doesn't matter. Okay, union infinity, then for every z here mod fz minus f infinity will be less than epsilon. If you want un, you know how to choose that. So what you do is choose a natural number which is greater than 2 by epsilon plus 1, etc. Okay, have you understood this? Okay, now let's look at a third example. Okay, I want to define f of z equal to az plus b by cz plus d. A, B, C, D are real numbers. Okay, now notice that, okay, oh, right. So I will assume C is not equal to 0 for the time being. Okay, we can explore a lot more, but I don't want to waste my time then, because then I will not get to what I want. That is not equal to 0, right? So I want to know when this is going to be continuous. Okay, and what are the values? So my thing should be cz plus d should not be equal to 0, therefore z should not be equal to minus d by c, etc. Okay, right. So I want to know when f is continuous. Okay, this is for z in some neighborhood of containing infinity. So I have to define what is f infinity. Right? What does your intuition say? Yeah, your intuition should say something. What should be the, so what should be the value? How to define infinity so that f is continuous at infinity? This is the question. Okay, I can do it here. I can actually solve this problem here, but rather I will prove an important result and I will come back to this. Okay, yeah. So we shall return to this later. Even though by same analysis we did, we can find out, because you can make a guess. All of you can make a guess, I guess. Okay, we shall return to this later. Okay, right. So I want to give an important principle. Suppose I have, let us have a pictures everywhere. This is my x, this is my y, and I have a function f. Okay, and this is a point x, this is a point fx. Okay, I want to know when f is continuous at x. Maybe, sorry, let me say y. Let me say, because that will look more natural, and this as z. Let me erase these things. So let this be a point y, and let this be a z, and this is the point fy, right? So f is a function from where to where? To topological spaces y and z. Okay, I want to know when f is continuous at y. Right? See, the point I'm trying to say is the topology of y or the open sets around y may be very difficult for me to visualize, because to prove continuity, what is that I have to do? I have to, if you give me an open set w here, then I have to find an open set v around y, so that for every y dash in v, f of y dash belongs to w. That is same as saying f of v is contained in w. Right? So finding that v may be difficult for me because the topology on y may be little looks more complicated, or I am not very comfortable with. Okay, but there is a beautiful trick. What I can do is, suppose, see, now you see the picture. This is very beautiful, right? Rectangle is always easy, right? So suppose there exists a space x and there is a homeomorphism phi. This is a homeomorphism phi. Then there is a unique point x which corresponds to y, right? Now do you see that I have a natural map from this is f composite phi. Yeah, right? So I'm going to say, what is that I want to claim now? I want to claim the following: f is continuous at y if and only if f composite phi is continuous at x. If you know a topology, this is a utterly trivial exercise. Okay, but this kind of thing is never taught. Okay, so let me go through that. Oh, okay, if you are very good, just ignore this next 5-10 minutes. Okay, just pause the video, do it on your own, and come back. Okay, this is very easy. Suppose f is continuous at y, then this is continuous. This way is easy because phi is a homeomorphism. Therefore, f composite phi, okay, is continuous at x, because composite of continuous function is continuous, right? What is this continuity? F by f composite phi at x is f of phi of x, that is f of y, right? Therefore, this follows. This all of you know. Composite of continuous function is continuous. So let us assume now. So we want to prove this direction. Assume f composite phi is continuous at x, right? Okay, since it's continuous at x, now you are giving me w, right? Then what do I know? I know there is an open set, a very beautiful looking open set u containing x, right? Therefore, there exists for the given w containing f of y, there is an open set u in x, okay, with x in u, so that f of u is contained in w. This is by continuity. Sorry, not f of, sorry, f composite phi of u is contained in w, right? Now let us look at what is f composite phi of u. That is f of phi of u. This is contained in w, right? Now x is in u, therefore fx, namely y, that is in f of u, call it b. Okay, right? Now since f is a homeomorphism, I know this is an open set in y. Since again I am sorry, phi of x, phi of u. Okay, this is, since phi is a homeomorphism. Okay, let me again write this. Right? Therefore, we have found an open set v in y with the point y in y, sorry, the y in v, so that f of v is contained in w. That implies f is continuous at y. Okay, understand? So pause, review, and proceed. The, but you should understand the principle. That's more important. As I said, the proof is extremely easy, right? Okay, so this is, if you want the picture again for this, I can, this may be my b, which is f of u. Okay, so what does it say? I want to prove f is continuous at y, so you gave me a w, then I have to find a v. So y may be a new object to me. Okay, but I know y is homeomorphic to some well-known object, or I am very comfortable with another topological space x such that x is homeomorphic to y. Therefore, the continuity of f at y is reduced to the continuity of the composite function f composite phi at x. Keep the picture in mind, relish it, and go through it. Okay. Now we will make use of this to prove. Okay. Let's revisit example 1. Okay. Before that, I want a homeomorphism. So let us look at the map phi from C infinity to C infinity. So defined by phi of z is 1 by z when z is not 0 or infinity, and phi of 0 is infinity and phi of infinity is 0. Okay, then I claim phi from C infinity to C infinity is a homeomorphism. Okay, that means first notice that phi, the phi composite phi is identity. Look at that. Why? Because if z is not 0, not infinity, phi of z will be phi of 1 by z. That will be 1 by z, which is z. And if z is 0, phi of 0 will be phi of infinity, but that is 0. And similarly, phi of phi infinity will be phi of 0, that will be infinity. Okay, therefore phi inverse is phi. So if I want to prove it's a homeomorphism, I have to say phi as well as phi inverse is continuous. And since I had already shown that phi composite phi equal to identity, even otherwise I know this phi is a bijection. Okay, since phi equal to phi inverse, okay, when I want to prove phi is a homeomorphism, it should be a bijection. Yes, that's correct. Then I have to then I have to prove phi and phi inverse both are continuous, but phi inverse is same as phi, therefore it's enough to show phi is continuous. Right, now to show it's continuous, start with any z which is not 0, not infinity, then phi is continuous. This is well known. Okay, and phi is continuous at infinity. That was example 1. Okay, and phi is continuous 0 is similar proof, but if you want, I will let's go through a proof. So let u be a neighborhood of infinity, then I have to find a neighborhood of 0, right? Find a neighborhood of open set. Okay, v containing 0, so that f of v is contained in u, right? Okay, now let us look at, so what is, so start with, see, when z equal to 0, f of z is already infinity, therefore that belong to v, that belong to u, no problem. Therefore let us assume z is not equal to 0, then what is f of z? 1 by z. I want it to lie in u, but remember any neighborhood of u is of the form v union infinity, where this V is actually set of all Z in C, so that mod Z is greater than some R and union singleton infinity, right? And since Z is not equal to 0, 1 by Z is not infinity, therefore thus I have to say that means 1 by modulus of this should be greater than R. That is same as saying mod Z should be less than 1 by R. Yeah. Therefore, if I take B 0 1 by R, then f of that is contained in U. Therefore, f is continuous at all of C infinity on C infinity. Therefore, sorry, again I wrote f. I'm sorry, this is phi, phi, phi. Okay, the map I'm considering is phi. Okay, I'm very sorry for this goofing. Okay, this since we already did phi, this is phi. Okay, therefore phi from C infinity to C infinity is a homeomorphism. Okay, now let's revisit examples. Okay, example 1. So my function was f of z equal to 1 by z for z in C star and equal to 0, f of infinity equal to 0. Therefore my open set was C star union infinity. Okay, I want to know whether f is continuous at infinity. What does it say? It simply said look at f composite phi whether it is continuous. Okay, what is the unique point which corresponds to infinity under phi? It is 0. Therefore whether this is continuous at 0, this is a question, right? But what is f composite phi of z? Okay, for z in some neighborhood of 0, f composite phi of z will be f of phi of z. Phi of z is f of 1 by z, but f of 1 by z, if z is not equal to 0, okay, f of 1 by z is z, and if z is 0, that is f composite phi at infinity. Of course this is f of phi of infinity, this is f of 0. Okay, sorry, f of 0 is what I have, f of phi of 0, which is f of infinity, which is 0. Yeah, you understand? Therefore f composite phi in a neighborhood of infinity, neighborhood of 0 is the identity function z going to z. This is continuous at z. Okay, you see that? Just to make sure that you understand, let's look at a second example. F of z, I will not keep writing what are the domain etc. Okay, z minus 1, right? Now this is continuous at infinity if and only if f composite phi is continuous at 0. Okay, therefore let us see what is f composite phi of z for z in near z in some neighborhood of 0. So let me assume z equal to 0, I will avoid. Okay, z equal to 0, we know the answer, so we will not do that. Okay, this is what f of 1 by z. So what is f of 1 by z? That is 1 by z plus 1 by 1 by z minus 1. So doing arithmetic, there is a z plus 1 by z, z minus 1 by z. Remember z is not equal to 0, therefore this is z plus 1 by z minus 1. And what is f of phi of infinity? We define it to be f of phi of 0, because neighborhood of 0, right? It is f of infinity, just we define to be 1. Okay, therefore near 0, okay, my function f of phi of z is z plus 1 by z minus 1, and at 0 it's equal to 1, and this is continuous at 0, obviously, right? Do you follow that? So you can take for any open ball epsilon where epsilon less than 1, because z minus 1 should not vanish for that. Okay, is this clear? Okay, now come back to the third example which I want to do. Okay, now let's look at f of z, az plus b. Last example will be special case of this, right? This is for z not equal to d minus c, and then I want to define f at infinity. Okay, how will I do that? Remember, at infinity as goes to 0, what will I do? I should expect a by c. This is what intuition says. Right? I do not know if this is correct or not, but let us see. So to check continuity, f is continuous at infinity if and only if f composite phi is continuous at 0. So what is f composite phi at z? That is a by z plus b by c by z plus d, that is a plus bz, again near 0, assume z is not equal to 0, a plus bz by c plus dz, right? For and what is f composite phi at 0? That is f at infinity, that we are defining to be a by c. Okay, is this continuous? Look at that. A plus b, a plus bz by c plus dz. As z goes to 0, what does it go to? A by c. That's correct. Therefore this is continuous at 0. Therefore f is continuous at infinity. Yeah, okay. So the last thing is going to play a crucial role in complex analysis. Okay, that trick, okay, the important trick which I taught you, how to use homeomorphism, okay, that one is going to play an important role to deal with point at infinity in complex analysis. That is why I said most often I don't need unnecessarily the so-called Riemann sphere, etc., since I know the topology or the open sets around infinity. How will I use it? Now suppose I have a function defined on an open set U containing infinity, which takes values in the complex plane. I want to know whether it is holomorphic on U. I want to define. Yeah, how will I define? My last principle, the important principle, gives an idea how to deal with it. Okay, that will be the point of our second session. Okay, I hope you all enjoyed. Okay, many of you who are bothered with point at infinity, etc., because of Riemann sphere and this and that, you see it's actually very easy. And this is all thanks to Riemann. Okay, because of him, next 100 odd years we developed topology. After 157 to 170 years, we can use it confidently and in a very simpler and conceptually easier way. Yeah, do you agree with me? We'll meet again.